All right, so all similar triangles, what can you tell me about the corresponding side lengths?
Would not preserve if it's similar. The angles are preserved.
Angles, but I was asking about side length.
The side length proportional.
Proportional means they're all in the same ratio. So let's say you were to have a 30, 60, 90 triangle, right? If you have a triangle, if you have a right triangle, it means you got what kind of angle? Right angle, 90 degrees, right? And in that right triangle, one of the angles is 30 degrees. What does that other angle always have to be? 60, right? They got to add up to the other 90. Does it matter how large or small that right triangle is? They'll all be 30 and then 60 and then 90. And you know already that all the corresponding sides are in the same ratio, right? Right? Like if I take the smaller 30, 60, 90 right triangle and do long leg divided by hypotenuse, would that be the same as the bigger one doing long leg divided by hypotenuse? If you simplified it, like lowest terms?
What?
Yeah, same ratio, right? Lowest terms, right? Fraction, ratio. I don't hear about popcorn. So all 30, 60, 90 triangles you agree are similar, right? Again, by what?
Angle.
Angle, right? No matter how large or small. How about all 45, 45, 90?
I'd say it is.
They'd all be similar, not the same, no matter how large or small, right? And all their corresponding sides, like hypotenuse divided by leg, would be the same result, wouldn't it? Like if you put it in lowest terms, they've got a decimal for that division. We've been doing that for quite a few weeks now, right? Yes? Do we agree? Okay, so no matter how big or small they are, they're going to be in the same ratio, these corresponding sides. And that would go the same for any right triangle, right? Say it has, let's say one of the acute angles in a right triangle is 20 degrees. What's the other angle, acute angle in that right triangle? One of them is 20. They have to add to what? One of them's already 90. So if one of the acute, one of them is already 90, the right angle. So if one of the acute angles is 20, the other one has to be what? 70 to add to the other 90. Does it matter how big or small it is? No. If one's 20, the other's got to be 70. And that would make, no matter how big the 20, 70, 90 triangle is, they'd be similar, wouldn't they? And all the hypotenuse divided by long leg of one would be equal to hypotenuse divided by the long leg of the bigger one, right? Everybody got that? Similar triangles in the same ratio. So these ratios of these similar right triangles are what we call trigonometry, right? And we have three main ratios that we look at, okay, depending on which angle we're talking about. The best way to present this is not exactly the way they're doing it, okay? So I'm just going to say, do this, and it's already on your notes page there. Is it just one note or two? All this one. Note number one. There it is. Well, first of all, before we get to the other part there, the third angle's theorem. You remember that, right? If two angles are congruent, one triangle to the other, what do you know about the third angles? They are congruent, right? So like I said, if I have a right triangle, one of the angles is what? 90. And if I said the other one was 20, right? And I got two triangles. One's huge, right? One's small. But they both have a 90 and a 20. What's the other third angle have to be?
70.
70, right? How big or small? The angles are congruent, they're similar, okay? So that tells us that they're going to be similar, and all their parts will be in the same ratio, okay?
Right angle.
By angle, exactly right. All right, so before we get to this part, let's just go back, and then I'll get to that trick part.
Probably just found it.
Found what?
The page.
You just flip through the pages there, okay? So let's take a look at these triangles. That's a 45, 45, 90, right? What's the ratio of the two legs to each other? What to what?
The ratio.
In this case right here. 7 to 7. With lowest terms, it'll be what to what? 1 to 1, right? Let's take a look at this differently sized 45, 45, 90. What are the ratio of the two lakes?
1 to 1.
But they're 5 and 5. They're still 1 to 1, right? You get that? Okay.
Be
How
like-
about over here?
1 to 1.
1 to 1. Doesn't matter how big or small that 45, 45, 90 triangle. Those lakes are always in the same ratio. And same with the hypotenuse, right? 7 squared to 2 divided by 7. Like that hypotenuse of the lake would be a ratio of what? 7 squared to 2 over 7 would just be the square root of 2 over 1, right? Or the square root of 2. No matter how big it is. Look at this one. 5 squared to 2 over 5 would be a ratio of what?
Square root of 2.
Square root of 2 to 1.
Holy crap, I got it right.
Okay, so yeah, not 2, right? Okay, so they're all going to be in the same ratio. So if we just call these legs X and X, wouldn't it work out the same? Right, whatever X is, what's the ratio of that leg to that leg? X over X. 1 to 1, whatever they are, okay? So the key to remember here is all 45, 45, 90 triangles are similar by angle, angle, right? Okay? That means their corresponding sides are all in the same what?
Proportion. Ratio.
Ratio, right? They're in proportion, same ratio, right? So corresponding sides in same ratio. No matter, you saw, no matter how big or small it is, right? If you pick any two pair of corresponding sides, whether it's a hypotenuse to the leg or leg to leg, they're always going to be in the same ratio, no matter how big or small the triangle is, right? And wouldn't that go for the one we were talking about, the 20, 70, 90? Right? No matter the size, okay? All right. So, when we're talking about sides, right, we're talking about sides in relation to a particular angle in the triangle, okay? It's called the reference angle, right? Reference angle. So before we start talking about the sine, cosine, and tangent stuff, which are the 3 ratios we deal with, there's 3 more, but 3 I didn't even know all ratios are all in the same lowest terms, right? So if I take this triangle, and I'm looking, it's a right triangle, you'll agree, right? And I'm looking at angle A, and I want to talk about the side opposite of angle A, right? That would be that side over there, wouldn't it?
Yep.
And if I want to talk about the side adjacent to angle A, it would be adjacent means next to, right? Okay, so it would be this side right here. Well, why wouldn't we call this side adjacent to angle A? Because it's next to it, right? Why don't we just call that adjacent? Any thoughts?
I would say it's because it's on a high, so.
It's already got a name, doesn't it? Even though it's adjacent, we call it the hypotenuse. How do you know where the hypotenuse is always? It's across from the what? The right angle, okay? So the hypotenuse, we never call that the adjacent because it's already got a name. It's called hypotenuse, right? Now, if I go over here to angle C, is the opposite side the same if we are looking at angle C as it was for A? No, it's just the side on the other side of the triangle. Now that's opposite, and this one becomes what to angle C? Adjacent, so it depends on which angle we're looking at, right? And right now, we're only going to be dealing with the 2 acute angles, right? We're not going to, for now, later course you will, be talking about the side opposite the right angle and adjacent and all that, right? Because that's just the hypotenuse. So right now, the acute angles. So if I go to angle A, that's the opposite side, and this is adjacent. If I go to C, that's the opposite, and now that's the adjacent. See how they switch, right? And if they're similar triangles, wouldn't the ratio of opposite measurement divided by adjacent measurement be the same in all of them? Wouldn't that ratio be the same on how big or small this triangle is? Right? Like up here. Look up here. See the 45, 45, 90? If I take this angle 45, and I want to talk about the ratio of the opposite side to the adjacent side, that would be what over what?
1 to 1.
1 to 1, or just 1, right? What if I took the opposite and adjacent in this triangle, still 45, 45, 90? Is it still 1 to 1? You see what I mean? So those corresponding side length ratios are the same, no matter how big, for 45 degrees. If you have a 45 degree angle, you know that the other acute angle must also be what? 45. If you have a 30 degree angle, the other acute angle must be what? 60. And no matter how big, the ratio of these corresponding opposite, adjacent, and hypotenuse are always going to be the same. They're kind of getting in. So now we just have to give some names to these, but let's make sure we can pick out opposite and adjacent and all that. So let's go down here. If we take example, and see this triangle here? What side is opposite of angle A? Name the side.
BC.
BC. We good with that? Number 2. Which side is the hypotenuse? See, the opposite, that one right there. Over here, what's the hypotenuse?
AC.
AC. Okay? And then the third one, which one is adjacent? I can't just ask you which one's adjacent. I got to tell you to which angle, right? I got to tell you which angle we're talking about. So which one is adjacent to angle C?
CB.
CB or BC, whatever, it doesn't matter. But by the way, which one's opposite of angle C?
AB.
AB. Which one's a hypotenuse?
CA.
Or AC, right? You get the idea? Okay? So that's how we find adjacent hypotenuse.
Yes. That's what I'm doing.
Yeah, okay.
It's trigonometric.
Mhm. So on the first page, we're talking about 45, 45, 90s, right? Let's go to 30, 60, 90s, because we've been dealing with those, right? Are all 30, 60, 90 triangles going to be similar?
Yep.
Yeah.
Oh, yeah.
So all 30, 60, 90 triangles are similar by what?
Angling.
Angle. And their corresponding sides will be what? In the same, okay, just say them, same ratios again of any other 30, 60, 90, right? Or 20, 70, 90, or 10, 80, 90, okay? So here's a 30, 60, 90. We're going to look at the 30 degree angle. Here's the opposite side to that 30 degree angle, right? And here's the adjacent, and this is always a hypotenuse no matter what. Even though it looks adjacent, it's only got a name, okay? So in our 30, 60, 90, okay, if I take in relation to the 30 degree angle, the small one, and I want to take the opposite side of any 30, 60, 90 divided by the hypotenuse, right? So it's like the short leg, isn't it? The hypotenuse. The short leg is x. You know that's 2x, right? So what's the ratio of opposite over hypotenuse? What over what?
X over 2X.
What cancels here?
X.
And you're left with 1/2 or 0.5. What? Don't the x's cancel? What 2?
Exactly 2.
Wouldn't what be 2?
No, because there's a 1 in front of the X.
Yeah, wouldn't the bottom one be 1 to get rid of one of them? 'Cause isn't
There's
the-
2 of them though.
What?
You get rid of the X's and then
Okay, but the bottom one has 2, and you get rid of 1.
Right, I canceled
it's
that
1.
one and that one. The only thing left then is a 2 and a 1. Remember, there's a 1 in front of everything. The x's cancel. Whatever x is, let's say it was 1 times 5. Hey, let's say it was 1 times 5 and 2 times 5. Wasn't that 5 over 10?
I've had an hour and 30 minutes of sleep. I don't
Well, answer my question.
Why did you not say
last night.
1 times 5 over 2 times 5 is 5 over 10, isn't it?
Wait, I'm sorry, what?
Let's say x
I
is,
can't understand.
let's say x is 5. What's 1 times 5?
5.
What's 2 times 5?
10.
5 over 10 reduces to what?
Okay.
1/2, because the 5's cancel. The x's cancel as well. Whatever, they might be at 5. Whatever. But 1/2, you know, as a decimal is what? It's right there. 0.5. Okay? Now, let's look at the ratio. Can you, hey, rotate. Let's look at the ratio
My popcorn's on.
from the 30 degree angle of the adjacent x squared to 3 divided by hypotenuse. Okay? So x squared of 3 over 2x, what cancels here? And what's left? Square root of 3 over 2. Now, as a decimal, you could put that in your calculator, and you get 0.8660. I would say traditionally in trigonometry, 4 decimal places is about how far you take them out, you know, when you're working with this stuff in the beginning, okay? Now let's take a look at the ratio in the 30, 60, 90, erasing.
So wait, we're finally finding what square root of 3 is?
Well, you could always find that because it's on your calculator. Sometimes we will. It depends on the question you're asked, okay? So that's not a bad question. So we've been keeping stuff in simplest radical form, right? Because we're kind of working in the abstract, right? But then math oftentimes is used to actually go out in the real world and do things, isn't it? Carter, I'm talking to you and answer your question, right? Yeah. I'm just going to proceed where I left off.
I was more.
So if I tell you I want you, like you're a contractor, right? And I say I want a concrete walkway in my yard, and I want it to be 8 squares of 3 feet long.
Who says that?
I did. I just did. I'm trying to illustrate a point.
Last year-
The point is, like, who says that, right? Because you have no idea. Like, how long do you really want this? Well, you would, okay, 8 times the square root of 3. Oh, decimal, you know. I want it to be about 10 feet
Wait,
long.
whose porch are we talking about?
Doesn't matter. We just, you follow me?
Yeah, this sounds funny.
So, if you have a specific application, you'll convert it to some useful decimal instead of leaving it in simplest radical form. But we leave it in simplest radical form for working in the abstract, right? Okay? None of what we're doing is dealing with lengths or anything like that, or specific applications. But when you go to specific application, you won't leave it as a square root of 2 over 2. What will you do? You put that in your calculator and get a decimal, okay? So trig now leads to a lot of specific applications. In fact, I used it just a couple of days ago when I was doing some in my garage. I had to figure out some side lengths. Now, if I do opposite over adjacent, right? Opposite of 30 is x. Adjacent is x squared to 3. That ratio is that. What cancels the x's, right? And I get 1 over the square root of 3. I could put that right in my calculator without rationalizing, get 0.5774. So let me ask you, for any 30, 60, 90, if I do the opposite of the 30-degree angle divided by the adjacent of the 30-degree angle, will it always come to 0.5774? No matter how big or small.
Yep.
It will, because they're all these triangles are similar, right? Does that make sense? Okay, that's the power of trig, right? So you're going to learn 3 ratios. You're going to get some of these ratios a name here in a minute, okay? What? So these ratios are all the same. We're going to give them a name pretty shortly. Okay. Now let's go to the other angle. Different reference angle now. 30, 60, 90, but now we're looking at the 60. So now the opposite and adjacents are different, aren't they?
Yep.
Okay. But this hypotenuse is the same, isn't it? Okay. So now let's look at opposite over hypotenuse for the 60. So what's opposite the 60 now? X squared to 3. What's a hypotenuse? That's the same, right?
Square root over 2.
So the x's cancel. You get the square root of 3 over 2. Put that in your calculator, right?
So if I can do it properly.
Hey, what was that the same as for the 30-degree angle? The adjacent over hypotenuse. So you went to, remember, because the opposite and adjacent switch now. So there's going to be some things that are same. And now if we go to from the 60, adjacent now is x, and hypotenuse is still 2x, so x over 2x, cancel, 0.5. Adjacent over hypotenuse for the 60, is that the same as something for the 30? The opposite over hypotenuse, right? Because when you're switching to acute angles, you're just switching opposite and adjacent, okay? And then the opposite over adjacent. Now that's going to be different, right? What was it here? X over x squared to 3 up here, right? But down here, what is it?
X squared 3 over
So it's a
x.
different opposite, a different adjacent, right? So now we get a totally new thing. They cancel, okay? And no matter how large or small these 30, 60, 90 triangles are, those ratios, when you put them in your calculator, will be the same, okay? These are called trigonometric ratios. And we're going to give these three ratios. See, opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. We're going to give a name, okay? We're going to give them a name. Now, in any triangle,
You also round to the nearest, I would say 10,000.
yes,
It just doesn't.
tenths, hundreds, thousands, 10,000s. Now, your calculator will give you these ratios. How does your calculator button know that one of these ratios is 0.5? Carter!
He's talking to me.
No! Ignore him then.
Yeah, he's not. He's lying.
How does your calculator know if you pick this ratio that it's always going to be 0.5? Because the triangles they come from are what? What? Similar. So that ratio will always be the same. Look at your calculator, by the way. You see three buttons on there, and if you have the blue one, it's in a menu. You should probably use a black one.
A black one.
You see three buttons that say, one of them says sine, or S-I-N, and then cosine, and then
I think
tangent.
that's dark blue.
Yeah.
Somebody, real quick,
Mine's the same exact one as this one, though.
whatever. Somebody put in the sine of 30 degrees and tell me what you get. Sine, parentheses 30, close parentheses. You got 0.5.
Really?
So this ratio of opposite over hypotenuse is called sine. Right? And we abbreviate
I
it.
just used the wrong button.
Let's go down here. Now,
Couldn't you just do that for everything though? Why did you have to write all that?
well, how are you ever going to know where it comes from?
What do you mean?
We'll need to know where it comes from to do other things. So anyway, when you have a right triangle and you do the ratio of opposite over hypotenuse to some angle, it's called the sine. We abbreviate SIN. It's not sin, okay? It's sine. Okay? The adjacent over hypotenuse is called cosine. That's just the name we gave it. And then the opposite over adjacent is what we call tangent, or TAN. Okay? Those are abbreviations. So by the way, this is the sine of 30 degrees. Got that. Cosine of 30 degrees. Just squeeze that in there. Tangent of 30 degrees. You always take the sine, cosine, tangent of an angle. Sine, cosine, tangent are just like ratios we were talking about. So this would be the sine of 60 degrees, right? 0.8660. This would be the cosine of 60 degrees, 0.5. And this is the tangent of 60 degrees. Okay? So what I think I want to do is change that note up a little bit. Hang on.
You said we're not covering everything that's gonna be on the pages. How are we gonna answer the questions?
I don't know. I don't know. I don't have an answer for that. Doing the best we can. Okay. Let me go to that notes page real quick. Note number 2 down here. Do you remember the variable you use for angles most of the time? What was that variable you use for angles?
Theta.
Theta, okay? So theta, we're doing trigonometry, we're going to call that our reference angle. Maybe it's a 30-degree angle, or we're referencing the 60-degree angle. Because remember, opposite adjacent change depending on which one you're referencing, right? You got that part? But the ratios are always the same. So the sine of theta, and this is actually, the full thing is sine, S-I-N-E, right? We abbreviate 3 letters, S-I-N, don't call it sin, okay? Is opposite over hypotenuse. Cosine, this is actually this, C-O-S-I-N-E, is the ratio of adjacent side over hypotenuse, that right triangle. Huh? Right, but it comes from cosine,
You got hand sign, I think?
C-O-S-I-N-E. Tangent, this is tangent, tangent. We abbreviate it, tan of the theta angle is opposite over adjacent, okay? All right? Let me see where they go with this. So I might come back to this in a second. Let me come here. Okay. Yeah, let's come back here. So these are the 3 ratios. Actually, 3 other ones you might learn when you get into like pre-calc and calc, right? But for now, it's just sine, cosine, tangent. That's it. And all they are ratios that are the same because the triangles are all what? Similar, right? Okay, let's go back to this.
Big number chart.
Big number chart.
Hey, I said that.
So we've got three ratios that exist for all of these triangles, right? And these three ratios, this is the basics of trigonometry. It's what it's all based on, okay? And it is just about the most useful math you've encountered so far, because it's used in the real world quite a bit, okay? So trigonometry now it connects our angles and our sides. So you haven't been able to do that before, right? So you've had Pythagorean theorem, but you need how many sides of the right triangle to find the third one? Two of them, right? Now you can just be given one side and some angle and be able to find everything else. Other angles, other sides, okay? So here we go. Here's sine, right? We abbreviate it sin theta, opposite over hypotenuse. You might have, here's the thing kids used to remember this. S equals O over H, okay? Cosine is adjacent over hypotenuse. Cosine, C equals A over H. And tangent equals opposite over adjacent. Tangent, opposite over adjacent. So here's, some kids like to use this to try and memorize this stuff, figure it out. So if these were words, could I say so, ka, toa? Have you ever heard that? What's this word here? So, ka, toa. So if you're trying to remember right now what cosine is, so ka, C-A-H, opposite over hypotenuse. You see what I mean? So you might use that to work that out. Now, your calculators you just saw will tell you what the sine, cosine, and tangent of any angle is, okay? When I was in school, we didn't have calculators that did that. In the back of all of our math books were a trigonometric reference table. So we had to look up the angles in a table, like you find over here. And this went on for several pages. Okay, this is just sampling of it. So the first column is your angle measure, in degrees. And the second, third, and fourth columns are the sine, cosine, and tangent of it. So why would the sine of 10 degrees be the same in any right triangle that has a 10-degree angle? Why would it always be that? Because if it's got a 90 and it's got a 10, the other angle by the third angle theorem is what? 80. Yeah, 80, right? So all of those would be what? All those 10, 80, 90 triangles would be what? Similar, which means all their corresponding parts are in the same what? Ratio. And there's that ratio right there. That makes sense? So whenever you have an angle measure, if you think of it coming out of the right triangle, it's going to have the same ratio, sine or cosine or tangent, right? Opposite over adjacent, adjacent over hypotenuse, the whole thing, okay? So here we did, and we had to look this up as a kid. We didn't have the calculator, wouldn't do it. On your calculator, or on your table, what does it say the cosine of 30 is? Cosine.
8.6.
0.8660. So on your calculator right now, press cosine 30, close parentheses, and hit enter. Tell me what you get.
0.88 or
8660 if you round it off correctly, right? And these tables are always rounded to 4 decimal places. Okay? Let's try tangent of 60 degrees. Tan 60, what do you get? 1.7321. Those ratios will always be the same. You didn't do any of that, did you? That's a shame. Okay. Right? Because any right triangle with a 60-degree angle will be similar to any other right triangle with a 60, and those ratios will be the same. You know, similar triangles are proportional. Got that part?
I put tangent 90 in for a second. 90 degrees, that's domain error.
Right. Remember, we're not going to be doing the 90-degree angle. We're going to do sine, cosine, and tangent of the two acute angles. So from 0 to 90. Well, not even 0, right? Now, the problem with these tables is, let's say I wanted the sine, cosine, of tangent of 20.3 degrees. Is that in the table? No. So when I was in school, to find that, everybody do that. Do the sine of 20.3 degrees. Calculator gives it right to you, doesn't it?
Yeah.
Okay. So when I was a kid, okay, I know between, we had to do this little method called extrapolation or interpolation, and it was all this proportionally solved, and I could find the sine of 20.3 degrees through some other calculations, which was really annoying. But we didn't know it's annoying because we didn't know something like this would exist, right? But you guys got it good. You got it easy. You don't need a table that's on your calculator. You can use this, right?
What grade
Calculator.
did you take geometry in?
Huh?
What grade did you take?
Well, they didn't teach trigonometry then. We had a class called trigonometry, which was after geometry, right?
Wait,
They
you
should-
don't have the class? It's algebra.
It used to be called Algebra 2 trigonometry, like slash trig, but they've taken a lot of most of the trig out of it, and they moved it to geometry, which kind of makes sense because aren't we dealing with right triangles?
Yeah.
Isn't that geometry?
No.
Yeah, shapes, right? Okay.
Is it-
So this is a table that will give you the same thing your calculator will give you, okay? Because all these ratios are the same, because any of these triangles are similar, okay? They'll be in the same ratio. Let's move on here. What's my time on this? All right, I have to make 2 videos out of this. So on the next page. So here's part of that table you had on the previous page, okay? So what are we doing here? Here's our reference angle theta, right? And they're asking you to find the tangent of theta, or the tangent here of angle A, okay, because that's theta. Tangent, and you need to remember these, it's the TOA part, opposite over hypotenuse. Well, what's opposite of theta in this case? 2.62. And what's adjacent? 2.20. So that ratio, 2.62 divided by 2.0, if you put that division in your calculator, you get 1.191. But you know that's tangent, right? We don't know what the angle is, right? So you can't really do that on your calculator right now, because you can tell tangent of what gives you that, right? But later on, we'll be able to use that to find what the angle is, using an inverse tangent, okay? We'll get to that in a minute, okay? But anyway, look at the table, though. Look at the table. Could you find this value in the table under tangent and work backwards? What does it look like it's close to here? Right there, doesn't it? So the tangent of some angle is 1.191. 1.1, that would be 1.192, but it's fairly close, right? And so what angle would that be? 50-degree angle. Probably a little bit more, right? Because that would round up to 2. But close enough, right, for government work. So that angle, you'd say, that's about 50 degrees, wouldn't you? Well, then that would say, they tell you what's the measure of that angle if this one's 50. They got to add to what?
40.
Yeah, 90, so it's 40, okay? That make sense? Okay? Here's one. Sine of 54 degrees. What over what? Opposite over hypotenuse, right? Well, I got this triangle with a 54-degree angle. Somebody's asking me, what's the ratio of the opposite to hypotenuse of that one? Well, it's going to be the same for any of these triangles with a 54-degree angle. So if we know the sine of 54, we can get the ratio of those 2 sides. What is the sine of 54 degrees? 0.8090, 0.8090. Whatever that side is, if I divide it by that side, I'm always going to get that number, no matter how big or small that triangle is. That make sense? Kind of? Probably when we start working with these, it'll make a little more sense. So let's do that. Let's now kind of use this, right? So here's how, and we have to figure out, well, how do we know if we're going to use sine, cosine, or tangent? Well, it depends on what they give you, okay? So if they want us to find x here, okay? You see this angle they gave us is 38 degrees. There's my x. X is what to this angle?
Adjacent.
Opposite, right? And this 12 is what to 38? That's adjacent. What trig ratio uses opposite over adjacent?
Tangent.
Tangent, right? If you get that memorized, you'll know, okay? So I'm going to use tangent here to solve for that missing side. So the tangent of this angle, right? So this is opposite, and this is adjacent, okay? So the tangent of this angle, here's my opposite, x. Here's my adjacent, 12. Got that? Equals x over 12. Well, how do I solve for x? It's being divided by 12, so what do I do to both sides? I multiply both sides by 12. What happens to the 12s here? Right? So I get x equals 12 times the tangent of 38. Well, what do you do from there? Got your calculator? Do 12 times tangent 38. Everybody do it right now. See what you get.
12 times it.
What does that say?
9.37.
9.38. Okay? Let's look at the next example. Whoops. A reference angle is this 16-degree angle. Let's see what they give us. What they give you tells you which function you're going to use, sine, cosine, or tangent. So for this reference angle 16, what side is that they give us?
Opposite.
And this side here with the x is the what? Hypotenuse. Which trig function uses opposite hypotenuse? Sine, right? So we get our equation like this. We know we're using sine, so we say the sine of 16 degrees equals 8, that's our opposite, over hypotenuse, x. Well, let me show you a little trick here, guys. Pay attention. Save you some time. If you ever have the x down in the bottom here, you can just switch these two things. You can switch them around. So in other words, take the x, put it here, sine 16, put it down here. So what we did? Just switch them. If the x is in the bottom, you can just switch the two things. I can show you the long way to do it, but remember that maybe, right? If the x is in the bottom, what can I do with these two things, guys? Switch them. So now I got x equals 8 divided by sine 16. On your calculators right now, do 8 divided by sine 16. 29. Did you get that right there?
No.
Yeah.
No?
Yeah, I got it.
Okay.
29.0236.
Right on the money. Here we go. Okay. And this one, here's our reference angle, 55. What side is this with the x on it? Adjacent. What side's this with the 18? What trig function uses adjacent over hypotenuse? Right, CAH. So that's how we get our equation. So now we can write the equation. Cosine of 55 equals x adjacent over 18 hypotenuse. How do I solve for that? What do I do to both sides? Multiply by 18. So I get x equals 18 cosine 55. They cancel, right?
Wait, can you just find like the cos and then multiply by 18?
That's the same thing, yes.
Yeah.
What's 5 times 3?
15.
What's 3 times 5? Same. Commutative property multiplication, right? So there you go. But it's just easier if you know, why do both two things? Just do 18 times cosine 55. Okay? Kind of getting a feel for it, right? Sine, cosine, and tangent for any given angle is always the same for that angle because it comes from similar triangles. Okay? Which you know are in the same ratio, of course. Right? Now, that's how you find missing sides. What if we want to go back and find missing angles? That means we have to undo sine and cosine and tangent. Okay? Probably going to need to. So I'm going to split this video because it's getting.